Hey everybody, this is your Stoichiometry review. You have a test tomorrow. Anyway, I'm going to go over some of these answers here and then solve some of the problems. If you take a look at this, first one, the branch of chemistry that deals with mass relationships between reactants and products is called stoichiometry. That's what we're studying right now. In a chemical reaction, the coefficients represent the number of moles of reactants and products. They are used to write mole ratios. Okay. Number three, what can you do with the mole ratio from a balanced chemical equation? Well, what you can do is you can calculate the mass of the product from a known mass of reactant. Now, these are all questions that are going to show up on your test tomorrow. Here's an example of one it's a version of what's probably going to happen in your test tomorrow. Same kind of idea, but different equation. In the following balanced equation, what is the mole ratio of hydrogen to ammonia? So you look at the coefficients in the balanced equation, and you can see there are 3 moles of hydrogen to 2 moles of ammonia. Okay. Down here, talking about limiting reactants. Excuse me. Recipe for s'mores, making 10 s'mores there. 10 graham crackers, 10 squares of chocolate, 10 large marshmallows, and in your pantry, what you would have would be 1 box of graham crackers, 5 squares of chocolate, and 30 large marshmallows. How many s'mores can you make with the ingredients in the pantry? Well, that would be 5. That's because there are 5 squares of chocolate and 1 square of chocolate for every s'more. See, 10 squares of chocolate here will make 10 s'mores. So 5 squares of chocolate will make 5 s'mores. And the chocolate is the limiting reactant in that situation. Okay, so now we get to some of this tough stuff. Well, not yet. Theoretical yield. This is calculated by a stoichiometry problem. The calculated amount of product formed in a reaction. Calculated. What you calculate using your stoichiometry flowchart and your calculator. Now, number 8, the limiting reactant. That's the reactant that determines the amount of product that can be formed in a reaction. It determines it. Okay, whatever's a limiting reactant, you can't have more product than that. You'll see that here in a little bit. Law of conservation of mass and what does it mean in a chemical reaction? You'll see a version of this tomorrow. The law says a mass can neither be created nor destroyed. And what does that mean? It means that the amount of product and the amount of reactant will be the same. Okay, law of conservation of mass. If you have 37 grams of reactant, that means you should have 37 grams of product. Law of conservation of mass. Number 10, we have students conducting a reaction in class, producing the data below. So you have the mass of an Erlenmeyer flask, the mass of the Erlenmeyer flask, and the aluminum nitride. So the mass of the aluminum nitride is found by subtracting those two. The 200 minus 154 grams. What you end up with is 46 grams. That is your actual yield. You were given in the problem the theoretical yield, okay? That was 111 grams. To find the percent yield, that would be your actual yield divided by your theoretical yield, which would be 46 divided by 111. Multiply that by 100, you get 41.4% yield, okay? Down here, you can see the equations for the equation for calculating the theoretical yield of magnesium phosphate if 15.4 grams of magnesium we start with. That is a mass-to-mass problem. You're going to have a lot of mass-to-mass problems to solve. You are given all the molar masses for all the substances here. And if you look at that, that is how you set up the equation. And you solve it, you get around 54 grams of magnesium phosphate. Okay. Then, this is a mole-to-mole problem. How many moles of bromine will be produced if 4.9 moles of aluminum chloride were formed? So aluminum chloride, that's our A. And we're going to find the moles of Br, that's our B. So A over here, B over here. So what you're going to do first, and that is moles. Let's put moles right here. You're going to go straight to the mole ratio. And your B is bromine, okay? And so you look at it, the coefficient for bromine is the 3. So the mole ratio says moles of B over moles of A. That would be 3 moles of Br2 over 2 moles of AlCl3. And you simply multiply the two numbers on the top and divide by the 2 on the bottom. And again, that's a mole to mole problem. Just one single step. That's a mole ratio. 13, how many grams of aluminum sulfide are produced from 6.7 moles of sulfur? Well, 6.7 moles of sulfur, and you're trying to find the grams of the mass of aluminum sulfide. Oops, that's wrong, excuse me. Al2, that's 3. So the first thing you do is you go straight into your mole ratio. That's first, moles of B over moles of A. And your B is going to be aluminum sulfide, 1 mole. Your A is going to be your sulfur, that's going to be 3 moles. And then you have one more step, and that is the molar mass of aluminum sulfide over 1 mole. And you can calculate it out yourself. Okay. The limiting reactant one we did cover in class. There are 2 A's to worry about. And we're trying to find our B here, and that's going to be that. So you're going to set it up like this. It's a mass-to-mass problem. There's one of them. There's one reactant. I just started with the nitrogen in this one. You're trying to find the mass of magnesium nitride for each one. You're trying to see which reactant is going to produce less magnesium nitride. And that's going to tell you what your limiting reactant is. And so the setup goes like this. You have the molar mass of the nitrogen right here. So molar mass of the N2, and 1 mole's over that. You have the mole ratio, which is next. And that's going to be 1 mole here and 1 mole here. Then you have the molar mass of your Mg3N2 over 1 mole here. Do the same thing with your magnesium, 4.7 grams of magnesium, 1 mole over the molar mass of magnesium. Then we have the mole ratio, which is next, and that is going to be 1 for the Mg3N2, and for the magnesium, that'll be a 3. Oops, my pencil's dying on me. I got to give it a little bit of juice. Give me a second. Oops. Takes only a few seconds to get a little bit of a charge. And we should be back in business. Okay. Molar, 1 mole of that over 3 moles of the magnesium, and then the molar mass again of the Mg3N2 here over 1 mole of that. When you calculate it out, when it's all said and done, I think this one is around, the magnesium is around 23.0, something like that, grams, and the nitrogen was around 46.5 or something like that, which makes the magnesium your limiting reactant, because you find which product, which one has less mass, and that will make the reactant the limiting reactant. Okay. Whenever you see, look at number 17. Whenever you see this kind of stuff like here, just cross it off. Okay. And now you can read the problem and it'll make a little more sense for you. Now, the last one I really want to worry about is this one, because I think you can handle number 15 and number 17, is your percent yield. To find percent yield, you're going to start with your 34.8 grams of CaO and the molar mass of CaO here, and 1 mole on top of that. Mole ratio is next, and that's going to be, hold on a second, put 2 over here. 1 mole on top, and we're going to put 2 moles of CaO on the bottom. My pencil died again. Give it a little more juice, because this is the last problem I'm going to solve. And that's going to have to do it. Okay, so 2 moles of the CaO on the bottom, and the 1 mole of the O2 on top. and the molar mass of the O2 on top over 1 mole on the bottom. Okay, your percent yield is going to be your actual, which is your 8.3 grams, over your theoretical, which you just calculated. I think the number comes out to be 9.9. 9.9 grams. When we do that, I'm going to multiply that by 100. I think it comes around to be 83.8% yield. Okay? And that's how you solve those problems. Good luck tomorrow. Have any questions? Give me an email. Bye.